Well, hello friends. Welcome back to Emulator Hacking. Today we are going to implement signal support in the user space emulator because that's something we've been ignoring until now. And what I mean by that is Unix signals, right? So if somebody presses Control C while something is running in the emulator, for example, the kernel will send a signal to the emulator to interrupt it, but we currently have no way of forwarding that signal to the emulated program. So that's what we'll be digging into today. And I guess we'll just start by making a simple test program. So call it maybe sig. And then let's put something in here. Well, we don't have to get fancy actually. We'll just do the interrupt signal and we will do something here like interrupted. And then sleep 60 return 0. Something like that maybe. So let's see. Oh, actually, I forgot to rerun my QEMU. No, my CMake. Dang it. It's so weird when you don't have the command you want to rerun in your bash history. Okay, so sig, Control C, interrupted. Very good. Okay, so the object of today is to make this run in the emulator. So if we run this in the emulator right now, what happens is we get an assertion failure because we don't support the sig action syscall. That's what it should say somewhere here. Unimplemented syscall sig action, right? So signal is just a wrapper around sig action, really. So we'll start by implementing the sig action syscall. And we'll see what we do with the inputs for that. So let's see here. I guess we can just put it up here. Sig action. I think it has 3 arguments. I want to say 3. Sig action. Yes, it does. Okay. So let's add a thingy. And that's the signal, and then there are 2 pointers actually. So it's like the new state, and then you get the old state of the signal configuration optionally written out to a pointer of your choice. So let's see what we do with this. This is the signal number, or I guess we can just call it signal. And then here is the, what are these things called anyway? Sig action. We have the signum, the act, and the old act. Right. So I guess we can call these that as well. It's kind of cute names. So let's see. So the thing here that makes this whole thing tricky with signals is that basically the emulated program is going to provide a function pointer, right? Like it's going to tell us where it wants to be called when the signal comes in, and we can't just forward that to the kernel like willy-nilly. We have to have some kind of translation layer here, right? Because the kernel can't call some emulator memory function address. So let's see. Maybe the first thing we should do is just sanitize the signal number. So let's see. Let's say that we can support like SIGINT. or maybe we should have a blacklist rather. So seg sig bus, I don't know, and sig kill. Actually, we can let you catch both of those. It might be a little bit weird to okay, let's just ignore sig kill. So if signum is sig kill, let's say that's not cool. Attempted to sig action, sig kill. Okay, and then sig action. So what is a sig action anyway? Sig action is one of these things. So it has a union of these two types. So these are the signal handler, signal callback, signal handler types. And then we have a sig set t, which is the mask of all signals, and some flags to go along with this. So really this member here is the spooky one. The rest is easy. The rest we can just forward. So let's see. So I guess we'll first thing we'll do is we'll just fetch this out. So host sig action, host act, and then we will do a copy from VM into host act from act, size of host act. Okay. So now we have the sig action struct, and maybe we ignore the old act for now. I feel like, I mean, we can't ignore it forever, but we could assert that, oh wait, no, signal returns to old signal handler. So we kind of need to deal with this. Okay. So my thinking is that we'll have to set up some kind of translation layer for signal handlers. So basically we need a signal handler in the emulator that catches all signals and then just sets a, hey, this signal came in flag somewhere. So I'm thinking we would have a Signalmask in the emulator object, maybe a sig set t, pending signals, something like that. And then let's see, so, and then we will set up signal listeners for this business. So let's see, setup stack, register signal handlers. Okay. Okay, so then we will just do this for all possible signals, I think. Do we have a constant for that? nsig, perfect. And sig action, we can call it sig actually, signum. And we don't care about the previous value, and then we'll do this, struct sig action act. Act SA handler is I guess Okay. Yeah, it returns void. Right, okay. So emulator the did receive signal signum. Okay. And actually, all this needs to do is just say pending signals, and we OR in the signal bit. Okay, so we OR in the signal. The pending signals is now a 32-bit mask where each bit represents a pending signal, and then we just take the signal number, shift it left by. We take a 1, shift it left by a signal number, and then we get the position in the pending signals mask. So we'll set that bit, and then we'll react to that somewhere. Don't know where yet, we'll figure it out. Okay, and then act SA, I think we don't need to mask anything, and we don't need any particular flags. Really, we can just do what signal does, actually. I don't know, do I really need to get fancy here? Maybe I don't. Maybe we can just call signal. Yeah, maybe that's good enough. I don't know why I thought I needed sig action. I'll put this next to setup stack. All right. Okay, so maybe we'll debug printf something here. Got signal. Signum. Can even ask for the name of it. Okay, so let's see that this comes in correctly. And there we go. And this, right, need to do something with that. So press Control C and wait. Got signal to interrupt. Right, okay. That's fine. So right, but that's still made the read call inside cat fail. So okay. That makes sense. So that's good. That means that we are receiving the signal there. So then let's assume that works correctly, and now we need to have a mapping here somewhere. Like our own little signal handler info. And I think signal handler info or signal handler and sig. Okay. And handler. Is this all that we need? I guess so. We could take all the other stuff as well, though. The mask and the flags. Why not? Dang it, I already forgot int flags. Right. Okay. So So if old act, then we are going to make a sig action and give him. So this is going to be a host old act. Handler is my signal handler, signum handler, and then I have to cast that to the type of this thing, which is some grotesque type, right? It's a function pointer to void takes int. Guess it's not so bad actually. Wait, what's wrong with that? Oh. There we go. Okay, and the mask is going to be 0, and the flags are going to be 0. Okay. And then we will just write these out to the old act pointer. So copy to VM, old act, host old act, size of host old act. Cool. So now comes the part where we cache this in the other direction. So signal handler signum. Oh wait, I wasn't supposed to zero these out. I was supposed to copy whatever was in the handler thingy. Right. Yeah, this is a little confusing, but we're gonna make it work. Yeah, something like this, and then we'll do the same up here. And we can actually rename this to old handler. Cool. Handler dot handler. So, wait, back up. What am I doing? Handler is going to be host act as a handler. This is the address in virtual memory that we have our signal handler at. And then we just copy over the other stuff. Signalmask. Okay. Yeah, this is starting to become clear. I don't know why this seemed kind of confusing for some reason. So basically, we don't forward to the kernel at all for signals. We're just going to handle signals internally in the emulator. So, I mean, we'll still receive signals from the kernel, but we're not going to let the emulator program communicate directly to the kernel about signals. We'll just handle that ourselves here. So that's what we're doing. And I guess we should also just say signum is less than 0 or signum is greater than or equal to and sig. That's not going to work. Clearly. Alright, so now that we have this, where is our main loop? Exec, right. So this is very, very similar to how you would implement CPU interrupts in a full system emulator, but now we're only a user space ring 3 emulator, right? But we still need to deal with these asynchronous interrupts called signals. So the way we do this is just after each instruction, we'll just check, hey, is there a pending signal? If so, we gotta transfer execution to a new place. And it needs to behave the same way that signals behave when the kernel calls them. So I think, maybe we can just do a call. But one thing is that, wait, how does this work? There's a sig return. How does this work again? We have a signal trampoline. So when a signal handler fires, then what we do is that we return from the kernel to user space to this little piece of trampoline code that stores stuff, backs up some stuff, and then transfers control to the signal handler. And then when we return from the signal handler, we make the special sig returns, is called, which restores a bunch of things. But I wonder if we can just simplify this kind of greatly here, because we are a user space emulator, we are never in kernel code. So we're always executing in user space. We'll see. We'll see if we can do this in a simpler way. So if we have pending signals, then we'll just figure out the first signal to dispatch. I think, I guess we can just go from bottom to top. What are the numbers? So we would start here. I mean, actually 0 is not a valid signal. So start at 1. Sig action. Shouldn't allow you to say 0. So like that. Okay, so 1 I and sig plus I. Call this the signal. The mask is this if m pending signals and mask. Then we have a signal. So then we will clear that bit in the pending signals, and then we will, let's just make a call. So can we do a jump set? Yeah, we can just, I guess we want to push our current address. So CPU EIP. Wait, why can't I do that? Oh, right. No? Right, the initialized stuff. Okay, so we push the EIP, and then we set EIP to signal handler sig. Oh, I guess we should call this signum handler. Okay, and then we can print something out here. Oops, excuse me. Okay, and we jump to msignal handler signum dot handler. Okay, so oh, we haven't implemented the sleep syscall. Okay, well, we can do that one. Int vert sleep. This one is easy. We will just forward it to the kernel. So, wait, it's seconds, not microseconds. There we go. And of course, we need to add it to the big chunky list here as well. Okay, that part was easy. Okay, so now we're in sleep. Press Control C, and what happens? We get signal 2 jumping to and then things get a bit messy. I guess because I'm not setting up the stack correctly for this, actually. That is true. So what were we doing in that trampoline? Let's see. So we say VBP, blah, blah, blah. Yeah, so this is actually, it's a little bit less predictable here, what we're doing. Wait. The trampoline. So this is used when we return from the kernel into a signal handler. Right. But what if we have a pending signal next time that we just schedule a thread? It was not in the kernel, it was just running in user space, and there's a pending something, and then control is transferred to here instead. Wait, how does that work? So we call setup stack. Okay, so we align the stack here. Right. Yeah. So we have to do all of this stuff. Okay. Yeah, I guess I'm not going to get away that easily. So, let's see, emulator. Exec. Okay, so here, let's say we put this in a helper. Dispatch one pending signal. Right, and we'll put that in a separate function here, otherwise this is going to get really unwieldy. Okay, and first thing we'll do is just compute the signal number. So we'll do it this way. So we'll break. All right. Have a little check here. Okay. All right. So now we got to do all of this stuff. Okay. I guess we can, maybe we can copy a lot of this actually, or most of it. Let's see, what does this stuff map to? So stack in our case is the ESP. Okay, so that's easy enough. That's just a CPU ESP value. At that point, okay, and then here we want to set ESP, shadow wrap as initialized. Minus the alignment adjustment. All right. Now, what is push value on user stack? That's just a straight push operation. Okay, that's easy. So that's the same as mCPU push 32. I guess our current E flags, which needs a getter apparently. Oh wait, this is not the right CPU. Okay. All right, we're gonna do this. And then we push the EIP. Yes. What was our old stack pointer? That was the original stack pointer before we started pushing, right? Of course. So that's fine. Also, these already have shadow, so we don't need to wrap them. So after EBX comes old ESP. SI and DI. All right, and then the old Signalmask. Maybe we'll ignore the Signalmask at the moment. I'm not sure. Well, we'll just push a 0 for that one for now. Makes me push old Signalmask here. Let's not worry about implementing signal masking right now. And then we push the signal number. This is the argument to the function, I guess. that's cool. And the handler address. Wait, what's going on here? We're pushing all of this and then we're setting it to the trampoline. And then the trampoline jumps to this place. Wait, man, we gotta cross-reference to what the trampoline is doing. Because this feels like the trampoline is gonna ret, but I don't... It's been so long since I looked at this. So this is where we enter from the kernel when we get a signal. And how do we call the signal handler? It's here. Okay, so push the signal code, call the signal handler, but we are stashing away EAX. Right, because it may contain a syscall return value because, because maybe we are on the trampoline because we just returned from the kernel from a syscall, in which case we will have a syscall return value in EAX that has to be preserved. Okay, so that's kind of messy. It would be nice if we didn't have to do that actually, but that's an entirely different problem. Alright, so do we need this? I mean, we do need something that... The trick is that we need to do the equivalent of a sig return. So we need a trampoline. Dang it. How do we normally do this? I guess we could just reproduce the trampoline somewhere as is. That works. So let's see. First up, let's just add this helper. So dispatch one pending signal, and then we'll also add, I think, the sig returns is called. Yeah. Sig return. All right. So the emulator. Okay. So we're almost at the end actually. So fine, this is just plumbing data to the trampoline. Handler and a 0. And then we can assert here that the CPU ESP value is now 16-byte aligned. Okay, and then what we need to do is just transfer control to the trampoline. Yeah, okay. And where is the signal trampoline? I guess we gotta set that up. So the trampoline will be something that we create early on in the emulator setup code. So let's see. Setup stack, register signal handlers, setup signal trampoline, let's say. make a region. And where do we put this? We'll put it at some weird address that nobody's using, like at the 2 megabyte mark, or, well, it's a bit weird. It's a bit too weird. We'll put it really high up for now, at boo. All right, and it only needs to be 1 page. Trampoline region, right? And then data, okay, so then we'll just copy this for now. Wait, how does this work here? Just borrow what this does. Yeah. Kind of ugly, but who cares? So you go here, trampoline region data. Okay. And we just need to remember the address of this thing. So trampoline, signal trampoline is at trampoline region base, and then we just register the region with the MMU. Okay. Let's see if that works. It would be amazing if we could just get that sigreturn syscall to come in. We'll see. Clickety clack. Unimplemented syscall sigreturn. Holy moly! And we got interrupted and everything. Cool. All right, that went better than I expected. So let's see. We got to deal with that sigreturn business. So let's add it here first of all. I forgot about that earlier. So this is a little bit hairier than I was expecting, I'll tell you that. I thought this was going to be... I didn't realize we would have to muck around so much with stack and preserving registers and stuff, but I should have known better. Okay, so we got sigreturn, and then we got to do what the kernel does essentially in the sigreturn syscall. So we restore the EAX what's going on here? Oh, this code is not written in a super obvious way. I don't really like this syscall, but I don't know if maybe there's a better solution for this. It feels really awkward that we have to call into the kernel to restore state. What is essentially user space state. It's just the fact is that I don't know how we would do this in user space. Let's see. Maybe it would be possible. I mean, everything's on the stack. It has to restore the Signalmask. That's like the one thing in the kernel that actually changes when you do a sigreturn. Maybe everything except that could be done in user space, and you could have a syscall just to update the Signalmask. That would be something, but we're not going to change that now. We're just going to mimic, so let's see. So we have to restore the state pushed by dispatch signal, indeed. Pop the stored blah blah blah. Okay, so first thing is we will grab the smuggled EAX from the stack. So smuggled EAX is and that's a stack access without actually popping, but there are 5 pops immediately after, so we can just pop and then pop 4 times more. We'll be fine. So pop 32, and then do it 4 more times. Or we can do this in the same way that he does, actually. Why not? Set ESP. Value. I forgot how these helpers work. Value with shadow. Shadow wrap with taint from. Right. You know what? This actually read nicer in this way, because it makes it like super obvious what's happening. So let's write it in the super obvious way, because that was my complaint about this code here, that this is all weird, because like you're popping but not changing the stack pointer, and then you're popping an extra time here to make up for that. Okay, so here is the signal mask. Maybe we should do this actually. Fine, we'll stash the signal mask here. Pop 32 value. Why not? I don't know that we'll do anything with it yet. But basically, if you mask a signal, then it shouldn't, we should ignore it if it comes in. That's the purpose of the signal mask. So that's just a pop here, effectively. And then we are copying out these registers, starting with EDI. So I guess we just do mCPU set EDI, mCPU pop 32. Yeah. So what were these? Popping ESP, now that's a bit of a spooky one. I guess that's one reason that we can't be... That's annoying. I guess that's why this code here is using an explicit stack pointer. Dang it. Okay, I see why this is written in this convoluted way now, because we have to actually overwrite ESP, so we can't be updating ESP because then everything gets out of whack. Alright, fine. We'll make a local pop here. So, local pop returns a value with shadow, U32. And I guess I have to put parens for that, don't I? Yes. Okay, so local pop is that we have a stack pointer. And smuggled EX is a local pop. And then we can do this in that silly way that he was doing, actually. Okay, fine. It's funny when you work with some old code that you've written, and you start to realize, wait a minute, this is stupid for a reason. It's actually necessary. Because it's so easy to shit talk your past self and say like, oh, you know, why is this way? This is so stupid and convoluted and blah, blah, blah. And then as you sit there and work with the thing, you realize, oh, I see. So it had to be this way. But we'll get over it. So, okay, so Here we just want to read from memory at that address. Read 32 at, oh wait, do we have MCPU read memory 32 at CPU SS and stack footer. Basically, return value, but not until we have actually incremented the stack pointer. Also, this is a raw pointer here, so we need to, this actually is a ×4 when it's in terms of bytes. So since we're not using a pointer but a U32, we have to go like this, essentially. That's okay. Okay. So what did we have? ESP, and then BX, DX, CX, and finally AX. And EIP should be stack footer, so that's where we return to. Is that it? So how is this gonna work? I guess we can just do it this way. Do we not have set E flags? Oh, okay. So we need a setter for that as well. Oh. And when we do that, we should probably untaint the flags. That's a bit annoying. So let's say that this is a value with shadow. And then flags tainted is E flags is uninitialized. Yeah, well, that's pretty good actually. So everything becomes restored, and then the sig return syscall returns to smuggle EAX. Very sneaky. All right. So this could actually lose shadow. Okay, so how did we fail? We got interrupted. That's good. And then I have an insertion failure at 118 in soft CPU. Update code cache fails. Wonder why. So let's see if no region, then let's just log something, right? Report. Or let's do it this way. No region found 4. Because this doesn't seem right. Okay, so we don't have a region for basically a null pointer. That's not good. So how do we end up in this situation? Can we maybe get a trace here? We could log all the syscalls. Because are we actually doing the sig return now? Let's see. Sig return happened. Returning to normal code at EAP with e-flags. I feel like I'm jumping over something somewhere, or like the stack is just not aligned correctly. So sig return happened, and we're returning to normal code here with e-flags. Very suspicious looking thing here, which looks like our code address that we should be in. Let's see what that actually is. Obj dump, userland sig. Oh, forgot some stuff. DZM Intel. Where is 8054 D9B? It is right here. So it's in sleep. We should return to the instruction after it's just called to sleep. That makes perfect sense. So we're just off by 1 on the stack. So how did we mess that up? Sig return. Okay, so smuggled EX, popping once, sure. And then we pop 4 more times. That's there. Signalmask. Oh, look at that. We didn't do a local pop here. That's what's messing it up. Duh. Boom. It worked. That's pretty cool. Alright, so wonder if that means we can run the shell now. No, still need some more APIs. Get p group. Maybe I wonder how much it would take to get the shell running. Well, let's see. Let's do some commits first of all, and then maybe we can look at the shell quickly. So we don't need that. Let's report that signals are happening. I feel like that's kind of relevant. So here, get PID, signum, stir signal, signum. All right. Trampolining too. Jumping, yeah. Handler at. Yeah, this will be good. It's nice to print something out when we get a signal, I guess. Maybe it's annoying, I'm not sure. Wait, that breaks? Why? Right, so I was working with this guy. Because we don't, cat doesn't register a SIGINT handler. So we need to handle that case as well. Like if there is no signal handler for for a signal, then we shouldn't try to dispatch it. Dispatch one pending signal, right? So here, if what exactly? If the, let's go here. Auto handler is this thing. Yeah, that'll be good. So handler is that, and so if handler is 0, wait, there's something like this, right? Yeah. So there's 0 and 1. 1 is ignore, 0 is default. So if handler is 0, so default, then we should just do like the default thing, which is different depending on the signal. So default signal action. I guess we can just do this. We already have this logic in the kernel, so we can borrow that here. And let's see. Okay, so we'll compute the default signal action is for the signal, signum. Okay, and then we switch on the action. Actually, I guess if it's ignore, we should ignore. Then we'll just return. Otherwise, let's crash, and then we can deal with that then. Because otherwise, it's either terminate, dump core. There is continue. That one is a little weird. I guess if somebody sends us sigcont, but I think the kernel takes care of that internally. That's not necessarily something we need to care about. I don't think. No handler registered. Yeah, so let's do that. And then here we will m shutdown true, return. Yeah. And if the handler is ignore, we'll ignore it. Alright, so that just, pressing Control C, that just exits the program. Wait, why was that not working right? Okay, I don't know what that was. So yeah. Got signal 2, interrupt, no handler registered, so the program exits. And because we exit abruptly, we don't deallocate stuff, so we see leaks here, which is pretty cool. Very, very cool, actually. So, nice. So I think here we have it. Wait, no region found. It added a little bit of extra debugging there that I don't need. Other than that, this is pretty good. Okay, so users say emulator. Support, add support for incoming Unix signals. Or let's say add support for Unix signals. The emulator will now register signal handlers for all possible signals and act as a translation layer between the kernel and emulated program process. We do to what? Get an accurate simulation of signal handling. We duplicate the same trampoline mechanism used by the kernel's signal delivery system, and also use the sig return syscall to return from a signal handler. Masking. Signal masking is not yet fully implemented here. Not fully implemented yet. But this is pretty cool. That is pretty cool. So yeah, so what was the thing about running the shell? I kind of want to run the shell now. Get pgroup. That one should be easy. We'll just add it. So let's see, get pgroup. How hard can it be to implement that one? Come on. Yeah, I mean, we'll just, that's just like a super dumb forward to the kernel kind of thing. You know what, I'll just put it at the bottom. What's the big deal? I feel like the current, it's going to ask me for more stuff. I mean, the shell is going to ask for more stuff. Shell is get pgroup. It also does tc set pgroup, which is an IO cuddle. That's fine. But it's going to whine about the IO cuddle because it's an unsupported IO cuddle 1. So is it this one? PIOC set pgroup? I bet it is. Well, we can implement that. So unsupported IO cuddle, sure. If request is, then what was the structure of using that? It's just simple integral, an integer argument, right? Yeah, it's just a pgid. So here we can just do return syscall CIO cuddle food request and the arc. TTY name. You want to know the name of the TTY we're running on? All right, I guess we can do that. So let's see, get pgroup. Space implement. Add the get pgroup. This is called. User space emulator. support IO cuddle TIC set grp. Okay, and then we need a TTY name. So TTY name we don't have. And how hard can it be? It's just a FUD, a buffer, and a size. And we can just actually forward it to the kernel. So let's see, emulator virt TTY name, FUD, flat header buffer, and U32 size. And then we'll make a host buffer with the same size as the size here. Call it buffer size. And then we will ask the kernel about this. So sc TTY name, FUD, host buffer data, host buffer size. And if there's any problem, we will just return the problem. Otherwise, we will copy over the stuff into the virtual memory. So, oh, wait, that's not how you do that. Should have made that a size T there. All right, and put these here. So TTY name. More things that don't work. Get current working directory. Alright, so let's just commit this one. Add the TTY name, syscall. And then we need get code. That one has 2 arguments, a buffer and a size. So get code. I think that's how it looks like. Get code. Yeah. Oh my goodness. A lot of complaining here. A lot of conditional depends on uninitialized data. Maybe we should, let's see. I don't know if these are bugs or if they are false positives. Probably false positives. We'll see. So I guess we can just turn that off for a moment and see if it starts up the shell. No, it dies at 385. Unimplemented syscall access. Alright. Well, we can implement that. So let's just do the code. The get code syscall. And for access, sys access, that's a path, a path length, and a access type. So flapper, size t, and int. Oops. Path length, and type. And then we will just go here and do that. Okay, so then we will copy out the path. Host path is MMU, copy buffer from VM, path length, right. And then we do int_rc is syscall, sc, access, host path, data, host path, size, type. And I think we can just do that actually. So it took a little while last time. Oh, more things does not work. Unsupported iCodel 2. Okay, so iCodel 2 is probably tcgetS. Who is doing a tcgetS? It is tcgetAdder, which makes sense that the shell would do that. Sure. I guess we can support that. No. Booger. Let me just commit those access changes first. Add the access, this is call. Okay, and then iocodel. If request is DIOC. Wait, which one was it? I don't remember. It was tcgetS, right? So this one will write out to a structure. So terminos, and we will do syscalls iocodel. Oh wait, I need to include that. Termios, as they say in Finland. So I guess pass the termios there, and then if that fails, return the failure. Otherwise, we copy to VM. Arg, termios, and size of termios. Yes. Oops. iocodel 3, which one is that? Is it setS, perhaps? Yes, of course it is. So here what we do is we just copy first. Copy from VM into termios, from arg, and then we do this, and that's the same, yeah. we are crashing in UTF-8 view. Well, I'm not gonna debug that now. So we're just gonna call it a day here, I think. So we didn't get the shell up and running quite, but we did at least get to a point where it asserts instead of saying like, oh, I don't have this syscall. So that's pretty cool. Support iocuddle tc get s and iocuddle tc set s. Okay, so I think this is going to be it for today's video. So if you made it this far, then I thank you for watching and for hanging out. I hope that you saw something interesting here. And oh shit, I turned off the reporting. I didn't commit that though, but I did turn it off. So that's why it doesn't show anything. I hope that you saw something interesting. I think this was very educational for me because it made me realize that signal delivery is not as trivial as I was expecting it to be. But we still got it done, got it working, so that's pretty cool. And maybe I messed something up and we'll figure it out later, but it's a start. So thanks for watching, and I'll see you next time. Bye.